Here you see the title. People have been fascinated by levitation always, and it appears that one can levitate micro objects. And we want to levitate whispering gallery mode microspheres. These are transparent objects which guide light by total internal reflection. And in 1 millimeter microsphere, light can run about 1 meter before it is absorbed and scattered. And yeah, about levitation, it's actual topic that in 2018 was Nobel Prize for optical tweezers awarded. Optical tweezers were invented already a long time ago. And the idea is that the transparent objects, they are pulled into larger intensity. And so it's light pressure. And photons get change in direction. So they give the recall to microsphere, and microsphere moves to the higher intensity. And the same happens in focus laser beam, that microsphere is pulled into focus into region of highest intensity. In Riga now is optical tweezers teaching it from Torlabs. We can trap transparent microspheres and cells in liquid. And for tweezers in liquid need high numerical aperture objective with numerical aperture larger than 0.7. And the best is with oil immersion microscope objectives. And
No problem. Sorry.
thank you, Aikars. To learn to work with optical tweezers, we went to Tel Aviv University in 2003, and this resulted in a joint publication between Latvian people and Israel people, and we studied the so-called vaterite. It's a ball-shaped form of calcium carbonate, and it has many pores, so it's not monocrystal. And here you can see in electron microscopy, and it is synthesized from calcium chloride and sodium carbonate. So it's easy to make, and it can be trapped in optical tweezers in ethanol, and we shine the light through the side. And what we observed was what we called nanojets, such shape in optical microscope. And basically this calcium carbonate microsphere, it acts like a micro lens, and it focuses light. Yeah, so with such small objects, we get so-called Meyer resonances that it is too small for whispering gallery mode resonance, but it scatters light in some preferred direction. And if shape is not symmetric, we get a micromotor. So we see that this particle can spin, and such battery particles, they are interesting for drug delivery. That one can deliver drugs and then dissolve battery with so-called photoacid, for example. And in Israel, another group was doing optical tweezers in air. They levitated oil micro droplets, and the leader of the group, Tal Karmon, he got his PhD from Caltech in Valhalla group. And yeah, he showed that liquid microspheres in optical trap, they are very round, and there is no surface irregularity. So he could get very high optical Q factor, 10 to the power 9. That means that whispering gallery mode resonances are very narrow. And when I came back, I wanted to repeat in Latvia. And then we learned that Doug Hanstorp is doing very similar things. He's trapping oil droplets in optical tweezers in air and put in electric capacitor with DC voltage, and then repeated the Millikan's experiment, oil drop experiment. And he shined ionizing radiation, which produced ions in the air, and they discharged this charged micro droplet, and micro droplet image was projected on a wall, distant like 1 meter away, and he could see that position on the wall changed in steps when electric charge changed. So this was some experiment which we can do in Riga. So I tested the trap with diamond abrasive particles, and here is the blue laser. And in air do not need high numerical aperture objective. You can trap with any objective. And afterwards demonstrated micro droplet trapping. Glycerol water mixture, there is pulverizer, like spray, and then droplets fall down in the glass tube. If they are too large, they fall through the focus and are not trapped. If they are too small, then air currents move them around too strongly. So one needs to find the diameter, which is about like 10-20 micrometers. And the idea was to make a dye laser in micro droplet, but it was unsuccessful. That this droplet, the dye instantly lost color. It was bleaching in 100 milliwatts focused beam. And so in optical tweezers, we could not do it. And then I remembered that there is nice way to trap charged particles in electrodynamic trap. For example, Wolfgang Paul got a Nobel Prize, and Hensch made such paperclip trap demonstration with charged dust 20 years ago. And now such traps are used in education. From Caltech, Kenneth Liebrecht makes nice movies on YouTube on such charged particles. And they are trapped with high voltage AC, 50 Hertz, and 5 kilovolts. And in Riga, I made several variations. Here is a trap with 4 rods, and we see charged dust particles that they make so-called ion crystals. They have all the same charge, and they repel from each other. And here is just a washer, and one can trap a single dust particle, or first trap many and then release, which has less charge, then they fall out. And finally, one can get only one. And this is like poor man ion trap. And it's good for demonstration. And the idea was to trap micro droplets from glycerol with dye, and then demonstrate dye laser action. And also we can trap diamond dust with nitrogen vacancy centers. And so these are traps from real life, ion trap, quadrupole trap, and pole trap. And basically one can get from one geometry to this geometry. If you bend the rods around, you get from this geometry into this geometry. And there are so-called Matthew equations which determine the stability, and for atoms, for ions, need frequencies around 10 megahertz, but for charged microparticles around 100 hertz. And this AC field makes so-called saddle potential. There is mechanical analogy. There are two equations, and here one has DC voltage, and this is radio frequency, and so the trap works also with 0 DC voltage. We are on this line, and for larger mass particles we need a smaller frequency. And these equations are the same for ions and the same for charged particles. And people nowadays want to make integrated things to put on a chip. So here is the geometry to put on a chip, single trapped ion. It can be used for quantum computing and optical clocks. And here is a do-it-yourself version that one can make a trap on printed circuit board like this and trap here the ions. And so I made similar trap and trapped these plastic microspheres, many microspheres or just single microsphere. And the idea is to trap a micro droplet, make lasing, but lasing power is in microwatt range, so it is actually too low for real life applications. Everyone needs milliwatts. And one of our students, he went to Innsbruck and became PhD student of Tracy Northup, who got PhD from Caltech. And they study micromechanical oscillators in vacuum, in electrodynamic trap. They give a kick to particle, and then it oscillates over a week. And they get extremely high mechanical Q factor, 10 to power 10. And oscillation frequency is just kilohertz. It's mechanical. And about particles, in Riga, I built now Wilson cloud chamber, and one can see fog. And if there is background radiation, we can see a track. And for this to work, need certain size of fog droplets. If they are too small, they do not fall down. If they are too big, they fall down very quickly, and these tracks don't show up for a long time. And I asked ChatGPT to calculate for two sizes, drop 1 micrometer diameter and 10 micrometer diameter. And what is interesting is that if we change diameter 10 times, the speed changes 100 times. So it is quadratic dependence. And yeah, it's the experiment like in university, there is dropping of balls in oil, and they fall by viscosity. They get terminal velocity. So here it's similar. And then there was a question why we do not see rainbow in droplets. And it appears that the droplets are too small for rainbow, and it's like a cloud. And in cloud, you also don't see rainbow. And since last year, I got involved in ion trapping experiment in Stockholm. So I was practicing with these charged ion things to understand better how it works. And we studied the negative tin isotopes. There are 10 isotopes in natural mixture, and there is isotopic shift of laser lines, absorption lines, and from that one can study nuclear size. And actually these transitions from S to T, they are forbidden for single photons, so they are very weak. And this unique trap allows to store same ions for 1 hour. They run around, and then it is possible to excite these forbidden transitions and get good signal. And recently I built a solar motor, which is with solar panels and the coil, and it is self-switching. When it turns, then another solar panel gets light, and then it's producing opposite magnetic field. And it was a question why Crookes radiometer spins so slow compared to such motors. Yeah, and by the way, this is levitating too. But this levitation is supported in one point. It's like here in Stjūņu, there was quasi-levitation. Yeah, and then the thing is same as yesterday, Andris Vaivod showed the tail of the comet. And the thing is that upon reflection from a spinning wheel, photon loses just a little bit of energy due to Doppler effect. And that's why these motors are so weak. And here we have photon absorption, and we have current which can drive a coil. And now I came to levitation magnetic field, and one cannot levitate with fixed magnets. It's so-called Earnshaw's theorem. But if a magnet is spinning on a motor, then one can trap another magnet. And there is nice paper by one scientist who studied 5 years and made different such calculations. Yeah, and I tried to repeat, and yeah, that works, of course. But then in Doug Hanstorp's group learned that more perspective is so-called magnetic levitation. If you place magnets like here, north-south, then in the middle is zero field, and the magnetic things are pushed to the region with zero field. And one can levitate graphite, which we can get from glassblower workshop or from pencil. And we tried to levitate diamond, but it did not work. So it's the same carbon, but different structure. So yeah. And Doug Hanstorp levitate micro droplets to study evaporation. In Riga, we would like to levitate their micro drop and demonstrate micro drop laser. And there is some curious thing about person who received the IG Nobel Prize for levitating a frog in a strong magnet. Frog has water and it's magnetic. And 10 years later, he received the real Nobel Prize for graphene. And with this, I have come to end. And my work is supported by Latvian Quantum Technologies Initiative. We are in this area, quantum sensors and devices, and work with photonics. Other people work with electronics. Their quantum particles are electrons, our quantum particles are photons. And this project is also for teaching, to prepare courses, demonstrations for students. And yeah, so thank you for attention.